Hello, everybody. Hope that you're doing well and feeling good after the weekend. Just going to start today with our section of notes about nuclear decay and half-life. So let's just sort of think back to what we've already covered. Certain isotopes of different elements are radioactive. They have a tendency to decay into what we call their daughter isotopes. And as they do that, they release particles and energy. And that's what nuclear decay is, the change of one element into another because of the loss of one of these particles. And we talked about alpha decay and beta decay. So what we're going to talk about today is something called nuclear decay rates and half-life. So if we have a radioactive isotope, we know that the atoms can transmutate into another atom if they release a particle. Well, how quickly does that happen? That's what we're concerned with today. So this happens what we call spontaneously. So whether or not a specific atom decays into the daughter isotope in any period of time is a somewhat random process when we look at an individual atom. Okay? But if we look at all of the atoms that are present in a sample, then we can start to predict how many of those atoms will decay and how quickly that sample will decay. And so often when we're talking about how quickly nuclear decay happens, we talk about the half-life of an isotope. Okay? And so the definition for the half-life is it's the amount of time it would take for half of the nuclei in that sample to decay. Okay. So if we look at this diagram here on the bottom of the slide, here we have a radioactive isotope, which is made of several atoms of this isotope. And at the beginning, all of the atoms are the parent isotope. If we look at what that sample would look like after one half-life has taken place, okay, what we'll notice is that about half of the atoms have decayed from the parent isotope into the daughter isotope, and that's what we see here in the middle. Okay, after one half-life, half of those atoms have decayed. In the second half-life, half of the remaining parent isotopes will have decayed. And if we were to move on to the third half-life, half of these remaining parent isotopes would have decayed. And we can continue that process, okay, until all of the parent isotope has completely decayed. But the thing is, we cannot say for sure, if I was looking at this specific parent isotope in one half-life, I can't really know, is it going to decay or is it not? I can know about the behavior and predict what all of these parent isotopes would do on average, but looking at a specific atom, I can't really be sure. I don't know if this atom is going to decay or not in the first half-life. There's a 50% chance that it will. But as we know, probability like a 50% chance. Sometimes it happens, sometimes it doesn't. You can't really predict that. Here on the far right, we see a animation that sort of shows 4 half-lives of this substance. Okay, and so in one of these, we're starting with many atoms of that substance. In the other one, we're starting with just a few. And again, we see that it's sort of a process that's difficult to predict, right? We can predict overall behavior of all of these atoms, but we can't know for sure what's going to happen to one individual atom. So how long does this take? How long is a half-life? Well, it depends on what isotope we're talking about. Okay, some radioactive isotopes have a fast half-life, Some have a very slow half-life. Some isotopes have a half-life that's measured in seconds or minutes. Others in years, decades, centuries, millennia. So it just sort of depends. Here are some common radioactive elements that are important in science. And so, for example, carbon-14 is a radioactive isotope of carbon that decays into nitrogen-14. It has a half-life of about 6,000 years. So if you had a sample of pure carbon-14, after 6,000 years, we would expect about half of that would be nitrogen-14 and half would still be carbon-14. So its half-life is 6,000 years. Potassium-40 has a half-life of 1.3 billion years. Uranium, 4.5 billion years. Rubidium, 49 billion years. So this varies significantly. So because of this idea that certain elements will decay over time in a predictable way, we can use this to help us determine time, to determine how old something is. Okay, we call this radiometric dating, radioactive dating. So let's look at how we would use this. Sorry, not sure what's going on there. Carbon-14 is commonly used in dating of organic material. Okay, so obviously carbon is hugely important in all living things, and carbon dating is used, for example, if scientists find a site of activity from human ancestors, they can take samples from that and they can use carbon dating to figure out when the wood that was used to build a fire, when that wood first grew by using this method of radioactive dating. Okay, so let's look at how this would work. So we have a table here. Okay, so if we look at our table, when we start off, when this substance, for example, was first formed, it had no half-lives had taken place because it was just formed. So all of the carbon-14 would have been present. After one half-life has gone by, again, we're going to estimate about 6,000 years, half of that carbon-14 would no longer be there. It will have decayed after 6,000 years. After 12,000 years, a second half-life will have gone by. Okay, and half of that half would remain for a fourth. That would be 12,000 years, and so forth. So we can repeat this process over and over again. And what we're seeing here, as the number of half-lives increases, the amount of the original carbon-14 decreases. And we can tie that to a certain period of time because we know the half-life of carbon-14 is around 6,000 years. So after 4 half-lives, there would be 1/16 of the original carbon-14, and then 1/32, and so forth. So if we ask some questions here, what is the percentage of carbon-14 after 2 half-lives? So after 1 half-life, 2 half-lives, there's 1/4 of the original carbon-14. That's 25%. Okay, often when I do these problems, I usually don't use fractions like this. I will usually use percentages, but you can use either really. What is the percentage of carbon-14 that would be left after 3 half-lives? Okay, think about that for a minute. Try to answer that question. So after 3 half-lives, you'd have 1/8 of the carbon-14 would be left. Okay, that would be 12.5%. And so as the amount of the decay product increases, what's happening to the amount of the original isotope? obviously it's getting smaller and smaller. If we had another column in this table showing us nitrogen 14, like if we go back here, remember carbon 14 decays into nitrogen 14 after about 6,000 years is the half-life. So we could also have another list in this column with the mass of the nitrogen 14. As carbon 14 decreased, nitrogen 14 would increase. So as the amount of the decay product increases, the amount of the original isotope decreases. So if a scientist were to find a sample of, let's say, a bone from some point in the distant past, they can analyze that sample. They can look at the ratio of carbon 14 in that substance to nitrogen 14, and by looking at that ratio they can tell about how old that thing was. So for example, if they were to find a bone and find that it's has equal amounts of carbon 14 and nitrogen 14, it's half carbon 14, half nitrogen 14, they would estimate that that bone was about 6,000 years old. Okay? If they had found a bone and they found that it was about 1/4 carbon 14 and 3/4 nitrogen, that would tell them it's about 12,000 years old, and so forth. Okay, so if we look at this with actual amounts of the sample, so here I'm telling you we started with 1,000 grams of carbon 14, and over a period of over a period of time, there was 500 grams left, so we can look at this. So after 6,000 years, one half-life would have gone by, and there would have then been 500 grams of carbon 14 because we started with 1,000 grams. And after another half-life, it would be 12,000 years, and half of that, 500, would have decayed into 250. And another half-life, 125, and so forth. So every time we're decreasing the amount by half. By 30,000 years, it would have been 5 half-lives. And what would the amount of carbon 14 been? 31.25 grams. So let's look at some other problems. So let's say we had a scientist had 100 kilograms of a sample of Durossium, the strongest and most beautiful element known to man. If the half-life of Durossium is 100 years, how much would be left in 200 years? So we started with 100 kilograms, and after 200 years, well, first, after 100 years, how much of the original Durossium would be left? Half of it, 50 kilograms. After another 100 years, half of that 50 would be left, 25 kilograms. So there'd be 25 kilograms of Durossium after 200 years. If we had a 200-gram sample of a substance, and it has a half-life of 50 days, how long will it take for that sample to decay to 25 grams? Why don't you pause the video and try to work this out on your own, then check your answer, see if you're right. So if you start with a 200-gram sample, its half-life is 50 days. So after 50 days, there'd be 100 grams of that substance. After another 50 days, there'd be 50 grams. And we need another 50 days. There would be 25 grams. So how long did it take to decay to 25 grams? 150 days. 50 plus 50 plus 50. Each time we're reducing the parent isotope by half. Okay, some more problems. Again, if you'd pause the video, do this on your own, see if you got it correct. Substance W has a half-life of 1,000 years. given a sample of 320 grams, how much would be left after 3,000 years? So we start with 320 grams. After 1 half-life, which we said was 1,000 years, we'd have 160 grams. After another 1,000 years, we'd have 80 grams. After another 1,000 years, there would be 40 grams. Substance X has a half-life of 20 years. So if we have 40 grams, how much would be left after 80 years? Okay, so we're doing this a little bit different. So we have 40 grams to begin. Okay, half-life's 20 years. So after 20 years, we have 20. 20 more, we have 10. 20 more, we have 5. 20 more, we have 2.5 grams. So after 80 years, 20, 40, 60, 80, we would be left with 2.5 grams of substance X. Substance Y, half-life of 50 years. If we start with 2,000 grams, how many years would it take to decay to 125 grams? So we just follow through the progression: 2,000, 1,000, 500, 250, and then 125. So how many years did that take? 50, 50, 50, 50, 200 years, or 4 half-lives. And then the last one, substance Z, is a half-life of 1 day. Okay, we start with a sample of 80 grams. How long before it's only 5 grams? Okay, 4 half-lives, which is 4 days. Now, rather than draw these boxes each time, okay, it's not necessary. Typically when I do these problems, I use a table. And I'm going to show you these same 2 questions, but setting it up sort of in a different way. Okay, so we have our same problems. What I typically would do was I'll set up a table like this. Okay, so we have, this is substance Y again. So I have the amount of substance Y, the number of half-lives, and how much time has gone by. Okay, so again, I set it up so I have 2,000 grams of sample. So my original amount of substance Y was 2,000 grams. Okay, and then I work through each row of the table. So at 0 half-lives, well, is 0 years. Okay, we have the original amount, 2,000 grams. Then after 1 half-life, we have 1,000 grams. That would take 50 years because 50 years is the half-life of substance Y. And after a second half-life, 50 more years have gone by, we would be left with half of that, 500 grams. And repeat this process, okay, until eventually I have the answer. Here's another example. Okay, so we're taking substance Z. Okay, after 4 half-lives, okay, is when it would get down to 5 grams. Okay, and that's a time of 4 days. So you could add more information onto this column. Sometimes you might also add a column showing the amount of the daughter isotope. Okay, so for example here, if we were to add that table, we'd have 0 grams because we start off, it's all parent isotope, it's all substance Y, and it would be 0 grams of the daughter isotope. And then after this would be 1,000, and after this would be 1,500. Basically, the amount of the parent isotope and the daughter isotope are always going to add up to the amount of your sample, which was 2,000 grams. So you could answer a bunch of different questions by using this technique. Okay, so I'm going to post, or I did post this video. This is just to reinforce the ideas of radiometric dating and how it works, and you could watch that video. I've given you an assignment with some half-life problems. And again, what I would like you to do is to do those problems. Okay. I've also posted a key, so check your work with a key. Be sure that you understand it. If you have questions about half-life or completing these problems, tomorrow we're going to have another Google Meet. So if you want to join that live, that's going to be at 11 o'clock a.m. If you can't make that, that's okay. You can email me with any questions that you might have, and I think then we should be good to move on. So I hope you guys have a great day, and we'll talk to you later.